Hi, my name is Lo Junming. This is my assignment 4B presentation, band structure of SMGA03 under 100,000 ATM. I will show the procedure that I followed, the optimization results, the band structure I obtained, and how I measure the band gap. Here's the objective and quick short summary. Firstly, I repeat the geometry optimization after applying the assigned external pressure, which is 100,000 ATM. This is the same step that I did for assignment 2. Secondly, I compute the band structure using the optimized cells. This is also the same step that I did for assignment 3. Thirdly, I measure and interpret the band gap. All of these steps, I followed the LED setup described in the course note, which includes the installation of cell file and power file procedures. Here are the software and key setup steps that I did for this assignment. I work in Ubuntu with CastStep as described in the setup notes. There are a few key steps that I followed. Firstly, I prepare a cell file with the crystal lattice and fractional positions. The crystal compound that I use is SMGO3, so I name the cell file as smgo03.cellfile. Secondly, I prepare a parent file and set the task to geometry optimization. I change the letter S to letter Z. Then I name the parent file with my name of with the crystal compound that I use, which is smgo3.parent file. Then I apply the pressure and edited the percentage block external pressure in the cell file and entered 100,000 ATM in 3 components, which is shown in the setup instruction. Then I run a CastStep.mpi command to do a geometry optimization. And after optimization, I copied the final lattice into a new cell file and changed the task to band structure. And lastly, I run a CastStep.mpi command again, and then plot with dispersion command and view my band structure in grays or Qt grays. Over here, these are the cell file, parent file, and the file that I got after I ran the CastStep.mpi command for geometry optimization. And over here, these are the cell file, parent file, and the files that I got after I ran the CastStep.mpi command for band structure. After I ran a CastStep.mpi file, I waited all the files download into the directory that I created, which is assignment 4. Then I open the CastStep file and look for the line that says geometry optimization completed successfully. And here are the geometry optimization results that I got. The following lines after that shows the optimized structure, like the software has estimated where the atom should be at the lowest energy. Here are my optimization outputs. On the left is the final geometry before applying pressure, and on the right is the final geometry after applying 100,000 ATM. Now, I will be comparing the before and after condition. The cell volume decreased from 60.85 to 57.36, a reduction of 3.5, which is negative 5.74%. The density rise from 7.32 to 7.76 gram per cm cube, an increase of 0.45 gram per cm cube, or an increase of 6.092%. The mass is the same, but the volume decreased. The enthalpy changed by 3.66 eV, which became slightly less negative. This reflects the work done on the system by external pressure and the change in internal energy terms. The bulk modulus increased dramatically from 160 gigapascal to 1615.5 gigapascal, indicating the structure stiffened under the high applied pressure. Here is the plotted band structure before and after applying 100,000 ATM. These are the bands plotted using the dispersion.al command and grays. Now, I will discuss the band structure I obtained for SMGO3 after applying 100,000 ATM. First, check the Fermi level. In this plot, the Fermi level lies between the valence bands and conduction band, so a band gap exists and can be measured. To measure the gap precisely, I use the plot's XY data. I double-click the curve to read the exact energy coordinates of the band extreme rather than just eyeballing the curve. Across the entire K-path, I identified the highest occupied state, the valence band maximum, and the lowest unoccupied state, the conduction band minimum. The values I measured from the plot are VBM equal to 6.53 eV and CBM equal to 11.037 eV. The band gap difference is equal to 4.507 eV. Importantly, both the VBM and CBM occur at the same reciprocal space point, R. I've circled the R on the x-axis and marked the two extremes. Because both extremes are at R, this is a direct band gap at R. That means optical transition across the gap are vertical in k-space and do not require a phonon for momentum conservation. Practically, this implies the material can absorb or emit photons efficiently at energies around 4.507 eV. A gap of 4.507 eV classifies SmGO3 as a wide bandgap insulator. At room temperature, intrinsic carrier concentration is negligible, so it will not conduct electrically without doping. The photon wavelength corresponding to this energy is deep UV, so the material should be transparent throughout the visible range. In conclusion, I applied 100,000 ATM and performed geometry optimization and band structure calculations. The geometry changed from 3.93 to 3.86. The cell volume changed from 60.85 to 57.36. The density increases from 7.32 to 7.76. The enthalpy changed slightly from negative 5,762 to negative 5,759. The bulk modulus reported large increase, 186.03 to 1,615.47 gigapascal. Recommend verifying the fitting procedure. The band structure. The valence band maximum is equal to 6.53 eV and the conduction band minimum equal to 11.037 eV. The band gap is equal to 4.507 eV, measured from XY data. Both the VBM and CBM lie at the RK point, which means it is a direct band gap at R. Interpretations. The SmGO3 at 100,000 ATM is a wide bandgap insulator, optically active in the deep UV. Direct transitions allowed and no phonon required. Therefore, at 100,000 ATM, SmGO3 shows a direct bandgap at R of 4.507 eV, consistent with a wide bandgap insulating behavior. That's all of my presentation. Thank you for listening.